Hello everyone, welcome to this presentation on serialization and JSON for Arduino. In this video, you will see the presentation that I did for the Maker Mind Meld Summit in December 2019. I thought it would be a good time to share it with you. Let's jump right in. Serialization and JSON, an introduction to serialization and JSON for Arduino users. Before we begin, let's verify that this course is really for you. The goal of this presentation is to discover JSON with Arduino. It is intended to beginners, but you need to be able to read simple C++ code. You must be able to write, you must have a basic knowledge of Arduino. In particular, you must be able to use the serial port. And you must know things like the loop function, the setup function, and includes and stuff like that. Let's review the program of the presentation. I will start by presenting myself, then we'll dedicate a huge part of the presentation to serialization. We'll start by saying what it is, and we'll see how we can implement serialization from scratch. And when I say from scratch, I mean without any library. Then we'll have a second large part on JSON. We'll see what JSON is, and also we will implement it from scratch, meaning without any library. And we'll finish with a presentation of ArduinoJson and see how it can improve and simplify our code. And I will end the presentation with a conclusion where I will talk about other serialization formats and compare them and give you some guidance on how to choose the right format for your application. So my name is Benoît Blanchon. I've been a professional programmer for 15 years. I'm the creator of the library ArduinoJson that we will see at the end of this course. And ArduinoJson is currently the the most popular Arduino library of all libraries. I'm also the author of other Arduino libraries like Arduino Trace and Stream Utils. Okay, let's start the presentation now. Let's start with serialization from scratch. I call this a rite of passage to fully appreciate JSON, and I'm pretty sure you will understand why. All that I will tell you in this part is based on a true story. It's actually based on my story, the story of how, as a junior programmer, I discovered the serialization techniques and how I improved my code to finally understand and appreciate the simplicity of the JSON format. So what is serialization? Serialization is the act of transforming the information into a series of bytes. Why do we do that? We do that to transmit the information or to store the information. That was the serialization. And the reverse part is the deserialization. Let me show you an example. Let's say you have two Arduinos. One has a sensor attached and the second has an LCD screen. And of course, you bind them with a serial link, and you want the information from the sensor to be displayed on the LCD screen. On the first Arduino, we measure the temperature, the humidity, and we get a timestamp that we serialize to use the serial port, whereas the second Arduino deserializes the content in order to display it on the LCD screen. Okay, now before showing you some code, I want to make sure that everyone is on the same page with the tool that I'm going to use. In particular, in the next slides, we'll write and read binary data to the serial port, and as opposed as text as we usually do. So it means that the function that we most often use, like serial.print, cannot work, because if I take, for example, serial.print int, if I pass the integer 42 to serial.print, it will send 4 and 2, the two characters 4 and 2. And that's not appropriate for our use case. Now, instead, we need to use serial.write. This function takes a pointer and a size, and will send the bytes as they are present in memory. So if to compare with serial.print, if I still have an integer that contains 42, serial.write will send the bits that makes 32 in binary. Similarly, we cannot use read string, and instead we must use serial.readbytes. And as you will see in the next few slides, we'll implement a serialization code incrementally. We'll start from something very basic and add the complexity step by step. We'll start with generation 1, then go to generation 2, etc. You get the idea. Let's see generation 1. We have 3 values to transmit. One is the temperature, it's a floating point value. Another floating point value is the humidity. And lastly, we have the timestamp, that is a long integer. Let's see the serialization code. We'll send the value, as I said in the title, one by one. So first I'm going to call serial.write, pass the address of the temperature variable and its size. The sign you see here, the ampersand, is an operator that says that returns the address of the variable. So in this case, it returns the address of the temperature variable, and sizeof on the other side of the expression returns the size of a float. So in this case, serial.write will send the content of the variable unmodified, just as it is. We do the same thing for the humidity, and we do the same thing for the timestamp. Let's see what goes over the wire. We have 4 bytes for the temperature, 4 bytes for the humidity, 4 bytes for the timestamp. So that's 12 bytes that goes over the wire. Let's see the deserialization code now. Similarly, we call serial.readbytes, as we said, and we pass the address of the variable so that serial.readbytes fill the variable with the data coming from the serial port. We do the same thing for the humidity, and we do the same thing for the timestamp. Let's see the pros of this approach. First is pretty simple. It's very performant. There is no effort made from the CPU. We are just sending the data as it is in memory. But the main problems are, well, it's very repetitive, and therefore it's error prone. In particular, we need to pay attention to sending the values in the same order, and we must take care of matching the address of the variable with the size of the type. Let's improve this code with generation 2. This is the 3 values that we have to send. Let's bundle them in a struct. Okay, this is our serialization code from last generation. Now that everything is bundled in a single struct, we can reduce this code to just one line. Instead of sending the variables one by one, we'll send the whole structure in one shot. Let's see the deserialization code. We can do exactly the same, read the whole structure in one shot. Over the wire, it's exactly the same thing that is transmitted. Let's see the pros of this approach. It's still very simple, even simpler than the previous one. The performance is excellent. It's foolproof. But the main problems are it's not portable, and we'll address this issue in the next generation. It's quite rigid, as you can see. It's not easy to add or remove members from the structure. Let's address the portability issue in generation 3. And what I mean by portability, I mean something that is written for one platform may not work correctly on another platform. Let's take an example. Size of long is platform dependent. On Arduino Uno, it's going to be 4 bytes. But on Linux 64, it's going to be 8 bytes. The solution to that is to substitute the type with a portable integer type. In this case, I'm using uint32 to store the timestamp instead of a signet long. And this type comes from the header stdint. As before, the same 12 bytes are transmitted over the wire. Now there is another portability issue that we will not address in this course. It's the endianness. Not all platforms stores the words in the same order. For example, let's take a long that contains 4 bytes. Well, some platforms will store the less significant byte first, where some others will store the most significant bytes, the bytes with the most weight. And so we have two schools. The little Indian school stores the least significant byte first, and the big Indian school stores the most significant byte first. So when system needs to cooperate, when they use different endianness convention, they have to reverse the byte before sending them over the wire. We won't do that today because I don't think it's really relevant for this course. Now let's see how we can improve our format by adding a string. This is our initial structure, our previous structure. Let's add a string. And for now we'll use a simple char array with 16 bytes. Remember that you cannot assign the string like this. You cannot assign a string literal to a char array. Instead, you must use strcpy that will copy the content of the string to the destination. Better, you can use you should use strlcpy that allows you to specify the capacity of the destination buffer, and this way it protects you against buffer overflows. Let's see what is sent over the wire. We still have 4 bytes for the temperature, 4 bytes for the humidity, 4 bytes for the timestamp, and now we added 16 bytes for the location. The problem here is that even if the string is very short, like 1 character, we are still sending 16 bytes over the wire. And see the pros of this approach. It's simple. It's portable, thanks to the uint32. But the main problems are it's pretty rigid. As we see, the maximum length of the string is 16. And there is a significant overhead. As I said, if the string is only 1 character long, you still need to send 16 bytes over the wire. Let's improve that in generation 5 with variable length strings. So this is our previous data structure. We'll move the string out of the data structure, and instead we'll store only the length in the data structure. Let's see the serialization code. First, before sending anything, we update the length of the string, and we call strlen with the string we want to send. Then we send the structure as before. After the structure, we send the string in binary. And we pass the length of the string so that serial.write knows where to stop. let's see what goes over the wire. So we still have 4 bytes for temperature, 4 bytes for humidity, for timestamp. Now we added 1 byte for the length of the string, and then we have the length of the string. In this case, I wrote 11 bytes, assuming that we are still using the same example, and this varies with the actual length of the string. Let's see the deserialization code now. So as before, we extract the data structure, and then we will read the string, but using the length that is stored in the data structure. We'll read exactly as much bytes as specified in the data structure. And after that, we append the null terminator to be sure that the location string is correctly terminated. Let's see the pros of this approach. There is no overhead, especially compared to the previous one. If we have to send one character for the location, we send just 2 characters. We send just 2 bytes, one for the length and another one for the actual character. The performance is still very good, but the main problems are it's very error prone. And in particular, you must remember to set the location len at the beginning to set the value in the data structure. And second, you need to add the null terminator at the end of the string. But we have a worse problem. What happens if someone sends you a location len that is larger than 16? Meaning that if you try to read, if you could read bytes with a value larger than 16, the buffer will clearly overflow, and this will crash your microcontroller. Another problem is that this is still pretty rigid. It's very difficult to add or remove or make some parameters optional. Let's see how we can improve that with generation 6. So this is our original data structure, original data format from generation 4. Imagine that now we want to make this format evolve, and we have 2 versions. The original version has 3 members, but the new version that I call version format v2 here has a new member pressure. If we want to serialize this, the most convenient way to do that is to bundle the two in a superstruct, and to add a version identifier. Here you see a version identifier as the first member of the data structure, and then a union that bundles the 2 versions in the structure. If you don't know what a union is, you can think of it as a struct, except that the members overlap each other's. So it means that format v1 and it means that the members v1 and v2 are at the same location in memory. You cannot use both at the same time. You must know which one is the right one. So that's why the first member of the data structure is a version identifier, and it will contain 1 if version 1 is to be used, or 2 if we are supposed to use version 2. Over the wire, for version 1, it will be the same as before, except that we add a byte at the front to say that it is version 1. For version 2, it's going to be the same thing, except that there is a new member at the end. So this is the format we want to serialize. Let's see the serialization code now. So first of all, we need to send only the version, and then we'll decide which one to send. If version is 1, we'll send only the v1 member. And if version is 2, we are going to send the v2 member. For the deserialization code, you're going to do the same. First, we'll read only the byte, the version identifier, and then if the identifier says it's version 1, then we are going to read version 1. Otherwise, we are going to read version 2. Let's see the pros of this approach. It's very flexible. Indeed, it's flexible because you can add as many versions as you need, and moreover, each version, each format doesn't have to share anything with other except except the version number. They can be completely different. You can use this technique to send completely different messages from one peer to another. Then the second good point is the performance. It's still very performant. There is very few effort from the CPU here. The main problems are it's quite error prone. You must manually select the right member of the union. You must remember to update the version number, and I think it's too complicated. And my reaction to this kind of code is it's really too much effort for daily programming. Let's take a break. So, where are we now? We wrote a serialization code that can store and send multiple values efficiently, that supports variable length strings, that can work across different platforms, that supports multiple versions, but unfortunately it got quite complicated over time. So it's time to take a different approach. And to me, this problem occurred at the time of the XML craze. So everyone was talking about XML. So, well, let's give this a try. Let's rewrite our serialization code with XML. Generation 7. So remember about our two version, format v1, format v2. Let's say now that those two structures are in fact XML document. So you should recognize the previous structures, and we can immediately see the benefits of this approach. First, it's very flexible. We can insert easily some members, make some optional. You can remove them, reorder them. There is no problem of portability by design. Since XML is a text format, you don't have to worry about the size of long, for example, and you don't have to worry about the order of the bytes in the words. It's not an issue with text formats. And that's something that is completely new now that our serialization format is human readable, which means that if you want to debug your program, you can easily look at what is transferred over the wire, and you can easily see if something is wrong. So my reaction to that is, wow, this is gonna be awesome. Let's try. So remember, this is the document we want to generate. This is going to be our serialization code. We'll start by writing the first fixed part of the document. And this time we are going to use serial.print because we want to send text. In this case, it doesn't change anything since it's already a string, but here it makes a difference. We send the temperature, but this time we send it as text. Instead of sending the bytes that really represent the floating point value 21.2, we send the 4 characters to 1.2. Then we send the next fixed part. We do the same for humidity, the same for timestamp, and the same for pressure. And we close the tag. Let's see what is sent over the wire. we have 6 bytes for the opening tag, temperature with the tags and the value takes 31 bytes, 23 bytes for humidity, 28 bytes for the timestamp, and 25 bytes for the pressure, and 7 bytes for the closing tag. That's a total of 122 bytes, which is roughly 6 times bigger than our previous code. So my reaction to that is, I hope it's worth it. It's gotta be worth it, right? Let's see how we can deserialize that. So this is gonna be our deserialization code. Here, before parsing the float, we need to put the cursor at the right location. And the easiest way to do that is to call serial.find. This function will look for the string that you specified. In this case, it's the opening tag for temperature. And as soon as it finds it, it stops reading, meaning that the things just after the call to serial.find is the characters from the temperature, 21.2. So we can simply call serial.parseFloat and it will return the value 21.2. And we can do the same for the humidity. So again, serial.find will scan until it finds the humidity opening tag, stop right here, and let us parse the float. We do the same for the timestamp. And if we find the pressure tag, remember that this one is optional, it's only on version 2, well, we parse the pressure. Okay, but there is a problem. This code with serial.find doesn't work if the order of the values change. Indeed, XML allows us to put the values in any order, and it's still a valid XML document. But if we do that, our deserialization format breaks, it falls apart. So how can we fix that? Yes, sure, we can use a library. How hard could it be, right? Let's try libxml2, which as far as I know is the most popular XML library for C and C++. And so this means that we just need to add the 2 following headers to our program. Let's do this. So first, before calling libxml2, I'm gonna read the complete XML document and put it in memory in a string, so it's more convenient. Then we are telling libxml to read the memory at this address. We pass the address of the internal buffer of the string, and for some reason we need to add this. I don't know why. Then we are going to take a pointer to the root element. In our case, it was called data, and we are going to loop through all children of the root. For each children, we'll take the name. We have to cast the pointer because for some reason libxml only stores unsigned char, and we need regular chars. We need to call this function to get the content of the node. Again, we need to cast. And now, if the name of the tag is temperature, we can read the temperature, and but we need to convert it because it's a string. So we call a to f. If you don't know what a to f is, it's a function to which you can pass a string and it returns a float. A is for ASCII, to f float. We do the same for the humidity, we do the same for the pressure, and we do the same for the timestamp. At the end of this iteration, of each iteration, we must free the value, which is the result of node get content. And finally, we must release the memory from the document by calling xml free doc, otherwise we'll get a memory leak. my reaction to this kind of code is yuck. Let's try something else. I think it's time now to introduce JSON, the fat-free alternative to XML. Let me tell you a story. The story of how I discovered JSON. So it was in 2005, and I was working on a JavaScript project, and I wanted to save the application settings somewhere, so I could load them when opening the app. Okay. So in JavaScript, you write variables like that, and in this case, I took our previous example. But you can also bundle them in an object, right? And what I discovered, what I realized, is that I could call eval like that, pass a string, and it will return the object as it is above. So it means that I could save this string in a text file and read the text file when opening the app and just call eval, and it will deserialize the code for me. It will mean, in this case, it means I don't have any deserialization code to write. So this is how I discovered JSON. By the way, if you are doing JavaScript nowadays, you can use JSON.parse instead of eval. Eval is really powerful because it will parse any JavaScript. It's much safer to use JSON.parse that will only accept JSON data, and it's probably faster too. Okay, of course, I did not discover JSON. Someone already discovered it before me, and this person is Douglas Crockford. He's very famous for writing this book, JavaScript, The Good Parts. In this book, he describes the JSON format, and also he is the owner of json.org, and he created this website in 2002. And you are probably wondering why I was not aware of that in 2005. And I must remember you that this was 3 or 4 years before Stack Overflow. So it was a really different era back then. Douglas Crockford described JSON as the fat-free alternative to XML. This is his own words. He says it's a lightweight data interchange format, easy for humans to read and write, and easy for machine to parse and generate. Let's see the details of the JSON syntax. What kind of data can we store in a JSON document? First, we have the simple values like the strings, the numbers, the booleans. Then we have the complex values like arrays and objects. Let's see strings in detail. Strings are surrounded by double quotes, meaning you cannot use single quotes, unlike JavaScript, and you cannot use a symbol without any quotes. JSON also supports escape sequences. In this case, I inserted a line break between the words hello and world. And it also supports Unicode. In this case, I'm using a Unicode escape sequence to use the little hat on the eye of my first name. All of this is very similar to C++. There is one exception though. JSON supports an additional escape character. Numbers in JSON. JSON only supports decimal numbers, meaning no hexadecimal. It supports floats values, and floating point values can be written with the scientific notation. All of this, again, is very similar to C++. Let's see arrays in detail now. Arrays are surrounded by square brackets. You can mix types in arrays, in this case an integer, a boolean, and a string. You can nest array, meaning that you can put an array in an array. And all of that is very similar to Python, except that you cannot put a trailing comma after the last value. Let's see objects now. Objects are surrounded by curly braces and use strings as keys. You can nest array in objects, and you can nest objects in objects. Again, this is very similar to Python, and again, there is an exception. You can put a comma after the last value. Now let's see some various stuff. JSON also supports null, which is very convenient to place an empty value, especially in an array. And JSON allows spaces, any number of spaces between each value, and it also allows line breaks and tabulation, which means that you can nicely indent your JSON document to make it more readable. So let's use JSON in our serialization code. Remember our two versions of our data structure? Well, now we'll say that the two, instead of two structure, we have two JSON document. And as you can see, the syntax is fairly readable. And we can immediately see the pros of this approach. It's flexible, almost as flexible as the XML format. It's portable, again, as a text format. It doesn't have any portability issue. It's not sensitive to the size of long, and is not sensitive to the byte ordering. It's human readable, as I said, but compared to XML, it's very concise. It's a very concise syntax. My reaction to this is, wow, excellent. I finally found the right format for my document. Let's write the serialization code. So this is the document we want to create, and this is going to be our serialization code. As for XML, we'll start by sending the first fixed part. Then we'll send the first value. We'll do the same for the humidity, the same for the timestamp, and the same for the pressure. And we'll close the root object. Let's see what is sent over the wire. We have 5 bytes for the root object, 18 bytes for the temperature, 13 bytes for humidity, 17 bytes for the timestamp, 15 for the pressure, and that's a total of 78 bytes, which is almost half as small as the version with XML. My reaction to that is yay! Let's see the deserialization code now. This is our JSON document. This is going to be our code. As before, as with XML, I'm going to use serial.find to find the beginning of the temperature value, and then call parse float. Do the same for humidity, do the same for the timestamp. If we find pressure, we also parse the pressure. But of course, we have the same problem as XML. We cannot change the order of the values, and also we cannot insert spaces. So that's going to be a problem. Okay, let's try with another library, but I promise this time it's going to be better. Let's see ArduinoJson, a JSON library for Arduino and all embedded C++ projects. Few words about ArduinoJson. As I said, it's currently the most popular Arduino library. I've been developing this library since 2014. It works not only with Arduino, but with any C++ projects. It's optimized for embedded platforms, in particular for low memory and low CPU hardware. And is very well tested with over 98% of test coverage. It's also well documented. You can find the complete documentation on ArduinoJson.org. Let's see how we can deserialize our document with ArduinoJson. This is our document. This is going to be our deserialization code. With ArduinoJson, everything starts with a JSON document. In this case, we are using a static JSON document, and I will talk more about that in a few slides. But for the moment, just imagine that this is going to be the location, the variable that will contain our document. Then we are going to call deserialize JSON, and as the name suggests, this function will deserialize a JSON document from the source. In this case, I pass the serial port as the source. Then we can extract the values from the document, and you see that we can use nice object-like syntax, and we don't need to specify the type of the value. We don't need to say, okay, extract a float, because ArduinoJson sees that temperature is a float and therefore deduces that it must return a float. I'm assuming here that we are still have temperature, humidity, timestamp, and pressure declared as previously. Okay, we can do the same for the humidity. Again, we don't need to specify that it's a float. ArduinoJson will deduce that. Same for the timestamp and same for the pressure. And if the pressure is missing, ArduinoJson will return 0. As a reminder, here is the code that we wrote by hand. I mean, without ArduinoJson. As you can see, with ArduinoJson, we get a shorter code. This deserialization code is not sensitive to the order, and also it supports escape sequences. Whenever you use a string, it will automatically insert the required escape sequences. Also, it supports nesting. Let me show you what I mean by that. I mean, you could extract a value inside another object like this, and you can chain the subscript operator to get a value nested in another object. Let's see now how we can serialize with ArduinoJson. Again, this is what we want to generate. This is our code. And again, we start with a JSON document, except that this time, instead of calling deserialize, we are going to build the JSON document in memory. We'll first insert the temperature. Again, we don't have to specify the type. ArduinoJson knows that this is a float, so it can do what's appropriate. We do the same for humidity, the same for timestamp, and the same for pressure. When our document is ready, we can call serialize JSON, and this function, as the name says, is going to serialize the JSON document and will send it to the destination. In this case, the destination is serial. As a reminder, this is the code that we wrote without the library. It's about the same length, but the new code is less error prone. Also, it supports escape sequences, as I said previously, and again, it supports nesting. As a demonstration, we could do something like that. We could chain the subscript operator to write a value inside an object. let's talk a bit about the JSON document as promised. So the JSON document contains the memory representation of the actual document. It's optimized for low memory and low CPU hardware. It contains a fixed size memory pool alongside with a blazing fast allocator. And this is really a unique feature of ArduinoJSON, where other libraries tend to use a lot of small allocations. ArduinoJSON makes only one large allocation. So the advantage of this approach is that the code is significantly smaller. I mean, the executable is smaller, is faster, and it doesn't increase the memory fragmentation. If you don't know what the memory fragmentation is, I recommend that you read the article on my blog, C++ for Arduino. There is also a YouTube video about that. So yes, the fixed size memory pool allows ArduinoJSON to be small, fast, and not prone to heap fragmentation. However, it requires a bit more work from your side, from the programmer, because you need to specify the size of the memory pool when you create the document. And we'll talk about that in a moment. The JSON document comes in two flavors: the static JSON document that we saw and the dynamic JSON document. Let's talk about those two now. Both have a fixed capacity. In one case, you must specify the capacity as a template parameter. In the other case, you pass a constructor parameter. So it means that for static JSON document, the capacity must be known at compile time, whereas for dynamic JSON document, you can set it at runtime. The static version allocates the memory pool with a simple byte array, whereas dynamic JSON document calls malloc and free. So this means that the static JSON document can and should live in the stack memory, whereas the dynamic JSON document puts its memory pool in the heap. If you don't know what stack and heap are, well, the stack is the location where your local variable lives. Like, for example, temperature, humidity, and pressure. They all live in the stack in our previous example. The heap is, or the free store, is sometimes called, is a more elastic area where you can allocate blocks of memory of variable size, and that's the location where, for example, the string class stores its data. So yeah, if you want a good explanation about that, maybe I can recommend you to read the Missing C++ course in my book. I will talk about that at the end of this presentation. So my recommendations for static and dynamic JSON document: for small document, prefer a static JSON document that can reside in the stack. It's faster, and yeah, there's no reason why you should use the heap for small size like this. When the document becomes larger, I recommend that you switch to a dynamic JSON document. And you can get, of course, more information on that on ArduinoJSon.org. So, how do we choose the capacity of the JSON document? On the one hand, you need it to be large enough to store any valid document. And what I mean by valid, I mean if you're running on an Arduino Uno with 2 kilobytes of RAM, it doesn't make any sense to try to deserialize a gigantic JSON document, JSON response from Open Weather Map, for example. I mean, small hardware, small document, and and I think every application has a limited scope of valid JSON document, and that's what you need to consider when deciding the capacity. So I insist in any kind of valid document. So on one hand, it must be large enough to store any valid document. On the other hand, it must be small enough to fit in the RAM. And ArduinoJSON provides two macros to compute the exact capacity. One is JSON object size. For example, JSON size 4 will return the size for an object with 4 members, and similarly, array size is going to return the size of an array. And on top of that, you need to add the size of the string that are going to be copied in the JSON document. And I know this is really complicated, and in practice we don't use these macros. So yeah, buddy, yeah, you're right, this is too complicated, but no, we cannot avoid specifying the capacity to the JSON document, but we can avoid the ugly computation. Let's see how. So if you go to arduinojson.org and click on the Assistant tab on the top navigation, you will see this page, and this is the ArduinoJson Assistant. This is an online tool that will help you compute the size of the capacity of the JSON document. You just need to pass your JSON document here, and the assistant will automatically compute the appropriate expression, and will also give you the actual size in bytes for your platform. So in our case, we just need 72 bytes for our JSON document. As a bonus, the ArduinoJson Assistant also generates two programs, one for serialization and another one for deserialization. And as you can see, both programs are very similar to what we wrote in this presentation. Well, that's all for ArduinoJson. And as promised, I'm going to talk about a few other alternatives. So let's see other formats. At the time I switched, the time we branched to use XML, we could have taken another road. We could have stayed in pure binary format, but instead of rolling up our own serialization code, we could have used existing binary formats like protocol buffers, Captain Proto, or Apache Swift. So these three formats are very similar. So in the next slide, you will see I'm going to talk about protocol buffers, but just in a word, it's a binary format, very similar to what we wrote at the beginning, but much more flexible. Another family of serialization format are binary JSONs. So, for example, we have message pack in this family, Bison, and Cibor. And they take the idea of JSON, but instead of using a text format, it's going to be a binary format. So, personally, I don't use these formats, and I don't recommend using them because you lose one big feature, that is the human readability of JSON, and well, the small gain you have in size and in performance doesn't outweigh the loss of the human readability. Another family of format are the extensions to JSON, and in this category we have JSON 5 and Hanson, which are basically the same. They add stuff like the hexadecimal integers, the trailing comma, the comments. So these formats are very handy if you use JSON to store configuration files. But I recommend against using them, because as soon as you generate a JSON 5 document, you are not generating a JSON document, so you lose the interoperability of JSON. So 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 the other Arduino, so the other JSON library will not be able to parse the document. Finally, we also have some stuff like Amazon Ion that adds types, new types to JSON. For example, it adds blobs to send binary data, and it also has dates, for example, and probably some others that I'm not aware of. Let's talk about the protocol buffer as promised. So as I said, it's a very flexible binary format. It offers a very decent speed. It's probably a little slower than our custom code, but I'm not sure. It has a very low overhead because it is able to compress things like even integers are encoded with variable length. So it's a smaller overhead than our serialization code, binary serialization code that we wrote in the first generations. And it works by defining the shape of the messages in a separate files in an interface definition file. This file shown on the right is a .proto file, and it describes the message that are supported by the program. In this case, I'm defining one message that contains 3 required fields and 1 optional field. And the rest is fairly obvious. Unfortunately, protocol buffers relies on code generation. So let me explain what I mean by that. So we have the proto file that is on the right here. To use that, you must call the proto C compiler, and this tool will generate C++ code. In this case, is gonna use the .pb.cc extension, which is just another extension for a C++ file. But the problem is that your program is already in another C++ file. So it means that you have to call the compiler to compile both files, all right? And then this will generate 2 object files, all right? Then you will have to call the linker, okay? And at the end, you will finally get your binary executable. So, okay. I understand. Some of you will say, okay, that's not a big deal. I'm just going to write a make file and everything's going to be all right. But unfortunately, most of you are probably thinking, what the hell is a make file? And that's the problem with protocol buffer. Because it relies on code generation, it has a significant impact on your build process. And well, my recommendation on that, protocol buffer is a good format. It's a very important player in the serialization game, but I think it's inappropriate for Arduino because it's too complex to set up. Now, to wrap this up, I'm gonna show you a table with the various formats that we saw today and give you my recommendation for your Arduino project. First, we saw the custom binary serialization format. We saw that it has a very small payload. It requires no effort from the CPU, so it's pretty fast. Unfortunately, it's not very flexible. As we saw, it's difficult to add several versions of a message, and it becomes quickly painful. As soon as you insert strings to the mix, it becomes quite complicated. So my recommendation is use this technique only for flat structures, for simple message with a flat structure without strings, and for isolated projects, because you don't have to take care about the portability and the interoperability issues. JSON has a payload that is significantly larger than than the binary format. That's expected. It also requires more work from the CPU, but at the same time, it's very flexible and it's very easy to use as soon as you use ArduinoJson. My recommendation on JSON is use it as soon as you have complex structures, and also use it to create APIs or to consume APIs. XML, you saw that the payload was gigantic. The work from the CPU is exaggerated, but at the same time, XML is the format that offers the largest flexibility, because we don't really dug into that, but you can add attributes to tags and stuff like that. But okay, it's so flexible, it's probably too powerful for our programs. And we also saw that the pain with XML is exaggerated too. And well, maybe I was unfair by using libxml, but come on, I didn't find any better alternative. So my recommendation on that, it's not suitable for embedded project, and I will also say that XML is not appropriate, is not a good format for serialization. Instead, I recommend that you use XML for stuff like actual document, like text document, like XML, or books, like EPUBs or stuff like that, but not for serialization. Then we saw protocol buffers. Protocol buffers have a very small payloads. They are very bandwidth efficient. They require very few work from the CPU thanks to the code generation. The format is extremely flexible, and but unfortunately, I think it's I put the pain cursor up to 6 because I think that the build process, the change in your build process is not appropriate for a simple Arduino project. So my recommendation on protocol buffer is use this approach for complex messages when performance matters. And for example, use this for remote procedure calls. Finally, message pack and other binary JSON format. We saw that the payload is a little smaller than JSON. The work from the CPU is also a little smaller. The flexibility is as good, but the pain, I think, is not as usual as convenient as JSON, because you lose the ability to just look at what goes over the serial port and say, okay, I can read the document, because you lose this readability aspect of JSON, which is very interesting when debugging. So no, I don't recommend using message pack or any other binary JSON. I don't think they represent an interesting compromise. So I'm gonna show you now the same table but in a graph. And on the y-axis, I'm going to show you the flexibility of the format from very rigid to very agile. And on the x-axis, I'm going to show you the pain of from happy programmer to, oh my god. These are where are the formats on the chart, and the size of the circle represents the performance. So as you can see, there is a large bubble for protocol buffers and binary, because they are the fastest formats. And what I want you to remember from this presentation is that, see how JSON is at the right spot. It's the easiest format to use, and it offers a reasonable flexibility with a decent performance. That's why I think JSON represents the best compromise, especially for embedded development. That's it for this presentation. If you want to learn more about ArduinoJson, again, you can go to ArduinoJson.org, where you will find the assistant, the API documentation, the examples, and the FAQ. If you want to support the project, or if you want to learn more about ArduinoJson, I recommend that you purchase my book, Mastering ArduinoJson. The book starts with a C++ refresher, where I teach you stuff like what is a pointer, what is a reference, what is a stack, what is the heap, how memory is managed in C++. And I had very, very good feedback about this chapter. So I really recommend that you check it out. The book also contains 2 large tutorials. Of course, there is one for deserialization, another one for serialization. The tutorials are very different from what we saw today. And the book closes with several case studies where you can see ArduinoJson in action. For example, there is a case study with GitHub, another one with OpenWeatherMap, another one with Adafruit.io. There is one that shows you how to recursively analyze a complex document. So yeah, and also it's a good way to support the development of the project. Well, that's all I had to say for today. I hope you enjoyed this video, and if so, subscribe to the channel, or check out my other YouTube channel, C++ for Arduino. Goodbye.